Let's practice finding the GCF, or the greatest common factor, together, but using 3 different methods. The first method I'm going to talk about is called the listing method. This one's the most basic and the easiest one to understand, but takes the longest. Basically, we're going to list all the factors of 45 and all the factors for 75, and then see which one is the greatest. So first we can go ahead and take this 45 and see if we can list all the factors. Now something that you could do to help with that is go ahead and use the prime factorizations, because that can help you come up with a complete factor list. If you take a look here, you're going to notice that we have a 5 and a 3 and a 3. So 45 is a prime factorization of, let's go ahead and write that as 45 is equal to 5 times 3 times 3. Right, and then let's take that 75 and go ahead and do the same thing. So 75, let's break that down. I think we can do maybe 3 times 25, and 25 will break into 5 times 5. All right, so we have our prime factors here as well. So we have 3, 5, and 5. So 75's prime factorization is going to be 75 is equal to, let's say, 5 times 5 times 3. So I wrote them bigger to smaller. Doesn't really matter as long as you have all of them. Right, now what we do is we go ahead and see if we can make a list. So for 45, we can start off with 1 times 45, and then there's no 2, but there is a 3 on the list here, so we can do 3 times 15. So 3 multiplied by 15 also gets 45. There's no 4 on the list, but there is a 5, so 5 times 9. That's going to be also 45, 5 times 9. There's no 6, there's no 7, there's no 8. I think we actually have all the factors for 45 now. For 75, let's go ahead and do the same thing. So we should start off with 1 times 75, that's a given, right? And then there's no 2, but there's a 3 and 25. So we can say 3 times 25 is 75. And then finally, I think there is a 5 times 15. So we're going to have 5 times 15, and I believe that's all the factors. So now that we have all the factors for 45 and 75, some of them they have in common, right? So if we take a look at this 1 and this 1, that's a common factor. This 3 and this 3, that's another common factor. These 5s are also common factors. And also these 15s are also common factors, right? So all of these numbers I just circled here, these are called common factors, right? We can split 75 and 45 into these groupings evenly with none left over. So what are the common factors? They are 1, 3, 5, and 15. Okay, now out of all of these, which one is the greatest common factor? Well, if we take a look, obviously, hopefully this makes sense, 15 is the greatest. So we can go ahead and say right at the end here that the GCF, or the greatest common factor, for 45 and 75 is equal to 15. Side note that's also pretty interesting is that if you can identify the greatest common factor of 15, that all the other common factors have to be factors of 15. All right, so that was the listing method. So let's maybe see if we can take a look at this prime factorization method. All right, so for this one, we're just going to go ahead and use their prime factorization. So if you look at above, we already found out the prime factorization, so I'm not going to make the trees again. I'll put them in order from least to greatest this time in terms of the prime factors though. So 45 is 3 times 3 times 5, and then 75 is equal to 3 times 5 times 5, right? And so when you're going ahead and doing this, all we have to do is by looking at the prime factorization, there's a slightly faster way to do this. And what we can do is see what do they have in common, right? So if we take a look at both of these lists, we can see that they both indeed have a 3, okay? And then both of these prime factorizations have a 5, right? So it turns out if you go ahead and multiply their common prime factors, so if we multiply this 3 times 5, that's equal to 15, then you actually don't have to do any more work, right? So just from that, just looking at what they had in common, it was this 3 and they both had a 5. Then you can go ahead and multiply 3 times 5, and we know the GCF for 45 and 75 is equal to 15, right? That's always gonna work. Just circle the common primes they have, and you don't need to list out all the factors. So if you look back at the first listing method, we can see that the GCF of 15 does match the GCF we just got here. And so we can also notice that in this case, we can also say that the GCF is equal to 15, but notice it was a little bit faster because we didn't have to list all the factors out and maybe miss one of them, right? We could just go straight to the prime factorizations and circle the ones they have in common and multiply them, okay? Finally, we have the ladder or the cake method. So this one is the fastest of them. So I'm gonna go ahead and show you what this looks like. So So for this ladder or cake method, all we do is we take the 75 and 45 and write them next to each other. And we go ahead and make either kind of like a step on a ladder or an upside down cake, however you want to think about it. And what's nice about this method is you just have to choose any number that goes into both of these numbers. So use your divisibility rules. I think they both end in 5, so I can divide them both by 5. So 5 times 9 would be 45. And then 5 times, I think 15 is 75. Again, you have to use some division, go ahead and do so. And then you have to ask yourself if they have any common factors still. And 9 and 15 are both divisible by 3. So we're going to put a 3 here. Looks like 3 times 3 would be 9 and 3 times 5 would be 15. And you know when to stop when these numbers at the bottom have nothing in common. So 3 and 5, they are called our relatively prime. Relatively prime. And if you're not sure what that means, that just means that the GCF between 3 and 5 is 1. They have nothing else in common, so you can't keep going at this point, okay? Now if we just go ahead and multiply these numbers on the side here, this 5 and 3 that are on the side, it's always the side numbers. Once you can't keep going anymore, that'll also tell us our GCF, right? So if you know your divisibility rules pretty well and you knew 15 went into both right away, then you could actually do this in one step as well. So this strategy is super helpful, especially if you are pretty good with your number sense and your division, and you can go ahead and do it in one step. So for example, if you took 45 and 75 and you knew 15 went into both from the beginning, you could totally just do one step and then you would be done, because this would be 3, this would be 5, and then so the GCF would be done right away, right? And no worries about the order which you do these in, because they're always going to work out the same way, because multiplication is commutative. But maybe you didn't start with the 5 like we did over here. Maybe you started with a 3. Then 3 times 15 would be 45, and then 3 times 25 would be 75. And then for 15 and 25, you can divide those both by 5. And if you do that, you're going to get 3 here, and you're going to get 5. And so you end up with the same thing with this 3 and the 5 at the end. And then you can see instead of 5 times 3, it's 3 times 5. But that's still going to get us the 15. So no matter how you look at it, you should still get the same GCF as long as you're dividing correctly. Let's try another example together. In this example, we have the two numbers of 64 and 80. Let's go ahead and try the listing method right from the beginning here. So for 64, let's see if we can list all the factors together. I'm not going to use the prime factorizations. I'm going to try to do this without it. So we'll start with 1 times 64, and then 2 times 32. There's no 3. 4 times 16. 5, nope. 6, nope. 7, nope. 8. I think 8 times 8 equals 64. I think that's it. And then for 80, what do we have here? So 80, I think we have 1 times 80, and then 2 multiplied by 40. There's no 3, but 4 multiplied by 20. 5 times 16. There's no 7, but there's an 8. I think 8 times 10. So I think these are all the factors for 64 and 80. So hopefully we have them all. And what do they have in common? Well, it looks like they both have 1, which makes sense because all numbers have 1 in common. Then 2, that's another common factor. 4 is another common factor. 8 is a common factor. And then 16 is a common factor. Right? So we have a lot of common factors here. So I'm going to go ahead and write this. We have a bunch of common factors. And there's several of them here. So let's see, what are all the common ways we could divide both of these numbers, 64 and 80, by? We could divide them all into one group, or 2 groups evenly, 4 groups evenly, 8 groups evenly, or 16 groups evenly. But which one is the greatest of them all? Looks like 16 would be the greatest common factor. And like we said earlier, if 16 is the GCF, these common factors are all factors of the GCF. Okay, so we can go ahead and say that the GCF here is equal to 16. All right, so we could divide 64 into 16 groups and 80 into 16 groups, and that's the greatest number you could divide them both by. So while that was the listing method, let's try the prime factorization method. This one is generally a little bit faster because you don't have to list all the factors, just the ones you need or the prime ones. And so for 64, let's go ahead and think about what this would look like. 64 is 2 times 32. 32 can divide by 2, that'd be 16. 16 can divide by 2, that'd be 8. 8 divided by 2, that would be 4. 4 divided by 2 would be 2 times 2. So at the end here, we have 6 2's multiplied together, that's 64. Now for 80, we can divide it by 2, that would be 40. You can take the half of that, and that would be 20. You can take half of that, that'd be 10. And finally a 2, and then a 5. So this would be the prime factorization for 80, right? Now, what do they have in common? Because again, greatest common factors are the ones they have in common. So we can take these 2's, that's one pair, that's a second pair, that's a third pair, and that would be a fourth pair. That's all they have in common here. So just go ahead and multiply how many things they had in common. So it was 4 of these 2's. So think about this, 2 times 2 is 4, times 2 is 8, times 2 is 16. So we can see here that the GCF here is indeed going to be 16. So we can go ahead and say the GCF is equal to 16. All right, it's the greatest common factor for 80 and 64. Now, just a little side note, if you're wondering how this works in terms of like, how do you know 16 is a factor? If you take this 16, right, and that comes from these 4 2's, and you multiply by 4, or these extra numbers, then you can see that 16 multiplied by the extra numbers of 4 here, 2 times 2, 16 times 4, that's going to equal 64, what we started with. And then you can look at these 4 2's, that's also 16. 16 times whatever leftover number, 16 times 5. So we go ahead and write it here, 16 multiplied by 5. That's going to equal the 80 that we started with. All right, so if you're wondering what the factor pairs are, that's what it's going to be. And finally, let's try out the ladder or the cake method here for this example. And so let's go ahead and just write 64 and 80 next to each other, 64 and 80. And I'll do this a few different ways just so you can see the different strategies, right? So just say you could only think of 2, right? And you know, half of 60 is 30 and half of 4 is 2, so that's gonna be 32. And then you know, half of 80 is gonna be 40. Then these are both even numbers, so you know you can still divide them by 2 again. So half of 32 is 16 and half of 40 is 20. And you're like, oh wait, I think I can divide these again by 2. Then you could say half of 16 is 8 and half of 20 is 10. And you're like, oh wait, I can divide these by 2 again. And then so 2 times 4 is 8, and then 2 times 5 is 10. And I think now 4 and 5 are relatively prime. They have nothing else in common. So on the side here, 2 times 2 times 2 times 2. These 4 2's multiplied together should give us our GCF. So let's see, 2 times 2 is 4, times 2 is 8, times 2 is 16. So we can say that the GCF does equal 16 here, right? Now, again, like that's if you're not seeing anything bigger, or that's just the first thing you thought of. If you can see bigger numbers, then you should absolutely go for it. That's the advantage of this method. So maybe you know your 8 times tables pretty well. So 8 times 8 is 64, and 8 times 10 is 80. And then you may also say, okay, 8 and 10 are even, so I can divide these by 2, and you get this 4 and you get this 5, and you're like, okay, 4 and 5 can't go anymore. They're relatively prime, their GCF is 1. So on the side here, this 8 times 2 also gets you this GCF of 16, but in a lot less steps, right? So if you see bigger numbers, you can go straight for that, okay? Another way you could have done this, again, there's so many ways you can do this one just because it has quite a bit of factors, but maybe the first thing you thought of was 4, right? If you thought of 4 to begin with and you knew 4 times 16 was 64, and then 4 times 20 was 80, you could have done that. And then looking at 16 and 20, you could have divided those both by 4, and 4 goes into 16 4 times, and 4 goes into 20 5 times. And notice how you end up in the same place, but you have 4 times 4 on the side, and that's still going to get us a GCF of 16, right? And if you're super strong with your division and you realized right from the beginning that these are both divisible by 16 because you happen to know your 16 times tables, or you did the prime factorization in your head pretty quickly, then you would know that this would be a 4, this would be a 5, and in one step you can get your GCF. And ideally that's what you'll be able to do in the long term, is do it in less steps. But again, all of these methods are fine as long as you can get the GCF, whatever works for you. So finally we can say the GCF here is 16, but again, just showing you 3 different ways that you can practice finding the GCF. And so you can see how the methods maybe kind of work together and see some similarities and differences, but these are 3 different ways for finding the GCF.